Okay, hi everybody here in the room and online. So let's get started. My name is Eleni Zirita Zaharatu, and I am an assistant professor here at HPI, leading the Spatial Analytics and Large-Scale Data Processing Research Group. So today I will talk to you about how databases handle spatial data and discuss some techniques for making spatial query processing faster. So it's not really an exaggeration to say that almost every piece of data that we generate today is tied to where it actually happened. If you think about your mobile devices that you're using all the time, most applications that you have there rely on location in some way. If you order a ride with Uber or Bolt, well, you have to share your location with the service so that they can match you with a nearby driver. If you post on social media, well, your post often includes a geotag and that can be linked to your location. So almost everything that you do with your mobile device leaves a digital trace that is linked to a location on Earth. Now, it's not, of course, just our mobile devices that generate spatial data. Thanks to the evolution of technologies like the Internet of Things, many cities today are becoming smarter, which means that we have multiple sensors deployed around the city, and these sensors collect information about the physical environment. So in any location in a city, you might have all kinds of information, like information about the infrastructure, about the traffic conditions, such as, like the buses that are passing by, the taxi, pickup rides. You can have information about the surrounding environment, like what's the weather condition, what's the pollution, or what's even the noise pollution if you have some like microphones in the city. So furthermore, a lot of scientific data and satellite images are also spatial, and this is data that can be quite massive in scale. For example, the European Union's flagship Earth observation program, which is called Copernicus, has satellites that collect roughly 16 terabytes of images every day. So on the slide, you can see how the size of the Copernicus data archive has grown from 2015 to 2021. And you can see it keeps growing and it's in the order of petabytes. And I checked last night, the latest numbers for the end of 2025, and it has already exceeded 80 petabytes. And this wealth of data is very important for many applications. Agriculture is a very big application of Earth observation data, but also scientists use such data sets for climate change research, among many other applications, of course. So in short, spatial data is practically everywhere around us, whether it's generated by us, people, or sensors, or produced through scientific research. So it's really important to have tools and systems and techniques that can manage and analyze such data efficiently. So now let's look at some very basic definitions about what exactly I mean when I talk about spatial data. And here on the slide, you see the main two spatial data primitives, which are point data, that are data objects that are entirely defined by their location. And we can describe the location with the help of a coordinate, of a reference coordinate system. So for each point, we just have its two coordinates in our reference coordinate system, x and y, if we are in a two-dimensional space. When we talk about spatial data, that also covers three-dimensional spaces. So then we just need the third coordinate, and we have x, y, and z to describe a point. Now, in addition to location, spatial objects often also have a geometric extent in space. So, for example, the extent of the building we are currently sitting at corresponds to the building area, so the footprint of the building on the map. So in most practical applications, you can represent the extent by a geometric shape, such as a line, for example, that would capture well roads or rivers, or a polygon that captures things like the area of a region. And you can see these two examples on the slide here. Now let's also talk about what a spatial query looks like. Here I show you the two most common and fundamental queries in spatial databases. The first one is a spatial range query. So here we have a set of objects, and I have a data set here that contains both point data but also polygons, so region data. And my query is also an area on the map. So this is the red query rectangle that defines a rectangular region. And we want to find all the spatial objects that intersect with that region. And as you can see here, in the query result, object 2 and 3 that are points are part of the result. The polygon object 1 is also in the result. But what happens with polygon data, it can be partially inside, partially outside our query region. But in that case, we just care about intersection, so it still intersects, so we return it as a result. But that's a difference between how point and region data behaves. Now, the other common spatial query is a spatial join, where here, similarly to a relational join, you have two data sets that you want to combine, and the spatial join retrieves a subset of the Cartesian product of the two data sets that again satisfies some spatial predicate. And again, this predicate could just be intersection, checking for intersection. So on the slide, you see a simple example where we have two data sets, a city data set, so these are the sea objects, and then a river data set with river 1 and river 2 in blue. And we just want to find which are the cities that there is a river passing through them. So we check for intersection between cities and rivers. And you can see again the result here. For example, river 1 passes through cities 1, C1 and C3. River 2 passes through C5. And yeah, there are a couple of cities that don't have rivers, right? So that's the result of the join. Now, if we think a little bit about how spatial data is stored, there are, in fact, two data models. And the examples I gave you so far belong to what we call a vector data model, which is the model where we represent spatial features with their geometries. These are the points, lines, and polygons I just talked about. But there is also the raster data model that you see here on the right, where we represent the area that we are studying with a collection of pixels, and each pixel has an extent, so it corresponds to a geographic area. So, for example, the satellite images that I talked about earlier are an example of raster data. And as you can see, if you look at this example, there is kind of an equivalence between the two representations. If you look here at the lines on your left-hand side, yes, there you see that these are rivers that we have as a blue line there. And then if you look at the raster data representation, you see that we have colored with blue color the pixels where, these rivers pass through. So you can kind of see the same physical phenomenon or physical object in these two different representations. But in today's lecture, we will only focus on vector data and how we can efficiently query and process vector data. So there won't be any more about raster data today. So let's go back to vector data and let's look specifically into polygons and polygonal data. So as I said, in real world, we use polygons to represent regions such as, for example, parks or national parks. And you can see a specific example here on the slide with a polygonal area of the Grand Canyon National Park in the US. What you can see here is that, this is a very large area of almost 5,000 square kilometers. But what's even more important to see is that we need really a lot of points in order to represent the boundary of that area. So in this case, this polygon has over 44,000 points or vertices. And this is important because of this complexity, then queries are also becoming very expensive. Why this is the case? Well, let's see what are the operations that we need to do if we want to evaluate the join and we have two polygonal data sets and we need to see if one polygon from one data set intersects with a polygon from the other data set. So what we need to do to check for this intersection is first we can run this like line segment intersection test, where essentially we check if there is a line segment from the one polygon that intersects with a line segment from the other polygon, which would mean that the polygons themselves also intersect. And for that, the best algorithm to use is the sweep line algorithm that has complexity n log n, where n is the number of vertices of the polygon. Now, if that test doesn't find any hits, we still need to do one more test because there is also the case that one polygon is full inside the other polygon, which would also qualify for intersection. And for that, we have to do a point and polygon test using the ray tracing algorithm, and that has complexity linear in the number of vertices of the polygon. So imagine before I just showed you a polygon that has 44,000 vertices. So these operations can become very serious bottlenecks. This is why we need, we cannot apply exactly the same techniques that we do in one-dimensional relational data, and we need to be smarter about checking for such spatial predicates when we evaluate spatial queries. So this is where the filter and refine paradigm comes in spatial data management. So the idea is that if we compare exact geometries, this is prohibitively expensive. So we want to avoid such expensive computations as much as possible. So for that, we evaluate queries in two steps. In the first step, we evaluate the spatial predicate that we have over a simplified geometry, so an approximation of the original geometry where we can quickly identify candidate results. And then the remaining candidates, of course, we still need to do the more expensive geometric tests in a step called refinement. Let me just show you a simple example to make sure we all follow here. So let's say we just have these two polygons, P1 and P2, and the query shown with red color, Q, and we would just want to run this as a range query. So we want to find all the polygons that intersect with this rectangular range. So what we do in the first step, instead of evaluating the query over the polygons, we approximate each polygon with a rectangle, and that's the smallest axis-aligned rectangle that fully encloses the polygon, and it's called a minimum bounding rectangle. So we evaluate the predicate now between these gray rectangles that approximate the polygons and the query. And here we see that we can already discard polygon 2 because the rectangle doesn't intersect with the query rectangle, but polygon 1, we find an intersection between the rectangles. So that becomes a candidate result. In this case, it's actually a false hit because the underlying polygon inside the rectangle doesn't intersect with our query, but we don't know that yet. So we go through the refinement, check, and now we compare the query with the actual geometry of the polygon. And in this simple case, we find that there is no intersection and the final result set is empty. So the idea here is that in the first filter step, we can do simple tests with simplified geometries much faster. And also, because this framework of this two-step filter and refine evaluation was proposed some decades ago, typically back then, these approximations of your spatial objects were stored on slow secondary storage. So it was also important to use space-efficient approximations that you can load fast, so for fast access. So that's typically a property you want to have. But if we look a little bit deeper into what kinds of approximations we can use for filtering, so in this first filter step, we can classify them in these two big classes. From the one side, we have conservative approximations. And the characteristic of those approximations is that they completely contain the original geometry. The minimum bounding rectangle that I just showed you in the previous example is the most widely and very the most common and almost like the one that's used everywhere approximation. But there are other alternatives that we have here. For example, we could, instead of having this axis-aligned minimum bounding rectangle, we could rotate it a bit to better match our underlying geometry. And this is a rotated minimum bounding rectangle. We could approximate the data with a convex hull. We have the 4-corner, the 5-corner approximation, or the minimum bounding circle, or the minimum bounding ellipsis. And the property of these conservative approximations is that they never miss a true result. but they can have false positives, as we just saw before. Now, on the other side, we have progressive approximations, and here it's the opposite. These are approximations that are completely contained within the original geometry. So, for example, here we have the maximum enclosed circle or the maximum enclosed rectangle. And the property that these approximations have is that they can confirm true positives, but they can have false negatives. And one last thing that I want you to notice on this slide is if you look again at the conservative approximations, here you see that we have also some numbers in parentheses. And these are how many values we need to represent each approximation. So, for example, the minimum bounding rectangle, it's very simple. We just need 4 values because in order to describe a rectangle, we just need the maximum values. We need to have the lower left corner of the rectangle and the upper right corner of the rectangle, and then we can draw the whole rectangle. So we need 2 coordinates for each corner. That's 4 values. And if you look at the number of values for the other approximations, you can see that there is kind of a trade-off here. Like for approximations where we use more values, we can also approximate the underlying geometry more precisely. Okay, so I have one more slide here to make sure that you understand the difference, like the different properties of conservative versus progressive approximation in terms of how we can use them for filtering. And let's look at an example with a minimum bounding rectangle as the representative for conservative approximations, where you can see we have a big polygon here that we approximate with its rectangle and a smaller one that we also approximate with a rectangle. And what can happen here is that we can have a false positive result. If the 2 rectangles intersect, that doesn't necessarily mean this is a result, because as you see here, the intersection happens at an area that is empty for the big rectangle. However, if the 2 rectangles do not intersect, then this is a true negative. We know for sure that the underlying polygons inside the rectangles cannot intersect. On the other side, for the progressive approximations, if the enclosed rectangles intersect, then we know for sure this is a true positive. We don't need to do any further checks. On the other side, if the enclosed rectangles do not intersect, well, this is a false negative because the bigger polygons around might still have an intersection. All right. So I hope that's clear so far. So now let's go back again to this 2-step filter and refine evaluation pipeline and ask ourselves, based on this evaluation framework, what do we need to do to make spatial queries run faster? Well, as I said already, what's really expensive, what's really the bottleneck in this pipeline is the refinement test that we have to do in the last step. And so our goal is to minimize such tests as much as possible. And conceptually, there are practically 3 strategies that we can follow to achieve that. Strategy 1, well, you want to increase the approximation of your filter as much as possible, the approximation precision, because more precise approximation means fewer false positives, so fewer results that need further refinement, so less work to do for the refinement stage. So that's on high level, that's one strategy. The other strategy is instead of trying to minimize the candidates that will go through refinement by using a single but very precise filter, you can add multiple intermediate filtering stages with progressively more precise approximations. So here, typically, you would start just with a rough filter that could be your minimum bounding rectangle as a first filter to eliminate obvious non-matches. And then in the next filtering stage, you can use a more precise approximation to further reduce the candidates. And it would be actually even better here if you use a filter that can also confirm some true hits. So if there are some results that you can identify just by using the filter, and you can keep refinement for those altogether. And the last high-level strategy that you could design around this evaluation pipeline is a little bit more radical, because that says that if the approximation that you're using for filtering is precise enough, then maybe you could just evaluate your queries on top of the spatial approximations rather than the original geometries, and then just directly return the final results. And for some applications, it might be sufficient to do that because maybe they don't care about fully precise query answers. But then if you do that, it would be at least good to have some quality guarantees about the approximation precision, so some tool that allows you to bound the error that you have here in these approximate answers. So let's now go through the plan for today, or at least the remaining plan for today. So we are kind of halfway through now. And in the remaining time, I would like to go into some more concrete techniques that use the insights I just presented for making spatial queries more efficient. So first, we will look at how we can make approximations more precise, and by doing that, we can do faster searches through a spatial index. And then I will talk about using GPU acceleration for evaluating spatial queries, and also how we can define distance bounds for enabling approximate query evaluation. So first, let me start a little bit with indexing and with some basics. So the most widely used or the most common index in spatial databases is the R-tree index that some of you might have heard about from your database classes. So it's kind of the equivalent of a B-tree, but for spatial databases. And I'm not going to go into the formal definitions, but the main idea here, and as you see with an example on the slide, is that we have some spatial objects and we want to group them together according to their spatial proximity, so that that objects that are close to each other can be packed together in one index node. And then when we have all the objects that we want to store in one index node, we represent the whole node, we summarize the whole node with, again, a minimum bounding rectangle that encloses all the objects that this node stores. And we kind of do that recursively. So when higher levels, so we build a tree, so higher levels of the tree are also minimum bounding rectangles that enclose the nodes, the children nodes, the extent of all the children nodes. So here you can see a very simple example where we have a root node with a black color, R0, which is a big rectangle that encloses all the objects that we have in our data set. And then we have divided these objects into two nodes, R1 and R2. And we represent all the data that each node has with a green minimum bounding rectangle. So what you see that is happening here is that these two nodes, R1 and R2, are overlapping a lot with each other. There is a big overlap region. And in general, that's not a very good property for an index, because if you have a query that falls in that overlapping region, then you cannot distinguish between the two nodes, and eventually you'll have to follow both paths of your index, and you cannot filter very well. And that's not a very useful index to have. So overall, when you're building an R-tree, you're trying to minimize this overlap between index nodes. For example, this layout here has less overlap than what we saw before. And we could even, if we allow the tree to be a bit more unbalanced, we could even eliminate the overlap between index nodes altogether. But here we might think that, okay, this looks good, and if we had one-dimensional data, that would be quite good. But when we have a spatial range query like what you see here with red dashed line, so again, this query says, let's find all the objects that intersect with a query region. When we try to evaluate, we start from the root node of the index. We check if that root node overlaps with our query range. Here it does, and then we check the children of the root, first going to R1, and R1 is the bottom index node here. And as you can see, well, the index node does intersect with our range query, but in fact, no object inside the index node does. but we don't know that without checking the objects themselves, since the node itself has an intersection. So here we have to go through all the objects inside node R1 one by one and check them for intersection. Here we don't find anything. Then we go to R2, where actually we have results to return. So this is a problem. So the fact that we now in the end traverse the entire index, although there were only 2 results in this case. And this happens because these rectangles are not precise. They don't approximate the underlying data very well. And if you actually look at an example with 3-dimensional data, there you can more clearly see the problem. So here on the slide, I'm showing you a node in an R3 index, but for 3-dimensional spatial objects. And what you actually see is that in this case, 97% of the minimum bounding box that encloses all the objects in the index node is actually empty. And that's not just one isolated node that happened to be very bad, but in our experiments, we observed, a big percentage of our index nodes that had a lot of, very high percentage of empty areas. So why this is a problem? Well, again, imagine that you want to evaluate the query, and now I'm showing you a query in 3 dimensions as this red box at the corner. Well, with 97% of empty areas, it can very likely happen that this query actually falls on empty portions of our index node. But again, since the query intersects with the rectangle that represents the data in the node, we don't know if the underlying data is a query result or not, so we need to go inside the node and check the objects one by one. And if I show you some numbers now, calculated over a real 3-dimensional data set, here on the slide I'm showing you a graph where I vary the query selectivity on the x-axis. So I have these 3D spatial range queries with high, meaning very few results are returned, medium and low selectivity. And on the y-axis, I measure the percentage of the leaf nodes of the R3 index that I need to access that actually contain true positives, so that contain actual results. And you can see that particularly for high selectivity, up to 64% of the leaf nodes that I'm accessing are false positives. I'm reading all the data in those nodes, but there are no actual results there are no results there. So this is kind of wasted work here. Now, what we could do about it, I showed you already for 2 dimensions that there are other more precise approximations that we could use. And I can also show you one of them. The convex hull is one of the most precise ones, and I show you here how that looks like in 3 dimensions for the same data that we had before. And as you can see, that's indeed much more precise, because here I'm reducing the empty space within the index node down from 97% to 37%. However, the problem here is that in order to represent this complex shape, I need 49 plus points. And I have this plus because I also need to store some information about how these points are connected. And this has 2 problems. I mean, first of all, the basic search primitives that we want to evaluate, like spatial intersection, is not so cheap anymore as it is for a box. So already, that a bit defeats the purpose of using something simple as a fast filter. And the other problem is it needs a lot more points. We need a lot more points to represent this convex hull. So we cannot have a very compact index with such a large representation. And on top of that, we need a variable number of points to represent the underlying data, because the convex hull, like the number of points we need, depends on the data distribution, depends on the underlying data. So it's not fixed. So again, that's not very easy to build an index around it. So an idea that we had in the past with my colleagues was quite simple. What we did is that we said, okay, minimum bounding rectangles are everywhere in spatial databases, and for a good reason, because they do have some good properties. They allow for fast intersection tests, and they are very compact to store. But they still don't have a satisfying precision. But we can easily increase their approximation precision just by subtracting empty areas that are inside the rectangles. In this case, I'm not going to go into details today, but in this case, as you can see in this 3D example, we can add 3 points, and that allows us to subtract away 3 areas from the box that are empty. You can see 2 here in the front, and there is 1 more that's you can less easily see in the back. And just by subtracting smaller boxes from the bigger box that are empty, we reduce the empty space by 45%, and that's a much simpler shape than what we had before. So that was one key idea. So with that, now let me move on to the next and practically last bigger topic for today, which is about using GPUs to accelerate spatial queries and then bounding spatial queries with a distance bound and enabling approximate results. So a common application for spatial queries is visual data exploration. Think, for example, of a city planner who wants to find patterns in urban data, and urban data is really spatial in nature. For example, a city planner might be interested in questions like, where are crime hotspots in the city? How does noise pollution vary in different neighborhoods? Which are areas that have a good public transport, and so on. So on the slide here, you can see a heat map visualization that shows the distribution of taxi pickup locations across different neighborhoods in Manhattan. So to generate this visualization, the visual system here needs to count how many pickups occurred within each neighborhood. And that's a spatial query, and we'll see the exact query in the next slide. But what's critical here is that typically when a user interacts with such a visualization system, they update their query parameters on the fly. So, for example, after looking at the distribution of taxi pickup locations over the different neighborhoods, maybe they want to zoom in and look at the distribution over different zip code areas, or they want to change the period of time that they want to analyze and stuff like that. So once they change a parameter of the query, that practically means there's a new query we need to evaluate, and we need to evaluate these queries fast so that this visual exploration is not disrupted. So overall, queries are generated at high rates in visual tools, and we need to evaluate them on the fly and at interactive speeds. So let's now see the query that runs in the background in order to calculate the heat map visualization that I just showed you in the previous slide. So this is what we call a spatial aggregation query. And as you can see, if we go through this query block by block, we can see that as input, we have 2 data sets. We have a data set of of many taxi rides in New York City, and which are points, because we just focus now on the GPS pickup location of the taxi ride. And then we have a data set that has the boundaries of the neighborhood areas in Manhattan. So what we first do here is that we also have a filter, because we want to filter the taxi rides only in January 2009. And then what this query does is that it maps each pickup location of a taxi ride to the neighborhood that contains it. And this operation requires performing a spatial join between the pickup locations of the taxi rides and the neighborhood regions. And then finally, once we know which are the pickups inside each neighborhood, we just count them and return the final result. Now, if we focus on the spatial join operation, which is the most expensive part of this query, this follows, like classic approaches, follow the filter and refine evaluation pipeline that I introduced today. So first, to calculate which are the taxi pickups inside each neighborhood, we just approximate the neighborhood polygon with the minimum bounding rectangle that encloses the neighborhood, and we just try to find pickup locations that are inside the rectangle. And then, as you can see here, we have some false matches, which are the red results, the red points on the slide. So then we actually need to eliminate them, and we do that by doing this point and polygon test that I also mentioned earlier today, where with that we can check if a point lies inside a polygon or not. Now, as I said, these tests have complexity that is linear to the number of vertices of the polygon, and real-world regions are very complex that have, in practice, hundreds or, as we saw earlier, even thousands of vertices. So these tests are quite expensive. And at the same time, we need to do these tests for a very large number of points, because typically point datasets like this taxi dataset have billions of points. So as a result, in fact, by using this classic filtered and refined evaluation strategy, we cannot achieve the interactive response times that are required by visual tools, because these tests are very expensive and we have to do a lot of them here. So to solve this challenge and achieve interactive response times, again, with my colleagues, we took a different approach, and we realized that we could abstract a spatial aggregation query as a graphics problem. So on a very conceptual high level, what we observed is that a spatial join between a point dataset, in this case, and the polygon dataset could be considered as just taking these two datasets and drawing them on the same canvas, and then we can use that canvas to find their intersections. And bear with me if that's not clear yet. I will walk through that step by step next. But why is this insight helpful? Well, that's because GPUs are highly optimized for drawing operations. The graphics community has been working on that for decades, trying to make these operations very fast on GPU hardware. So we want to, here we want to leverage that for evaluating spatial queries. So basically what we want to do is we want to use the GPU for drawing. And when you draw on the GPU, you don't have a blank white canvas, but you have pixels. So it's a pixelated canvas. And so now we will start drawing. And as a result of that, computing our queries, we will see. And in the first step, our approach that we call raster join draws the point dataset. So here I draw the first point from my dataset, and what I do is that as I draw the points, I can also keep track of the points that I'm drawing in each pixel of this canvas. So here it's just one point. I draw another point, and again I'm like increasing the counter for that pixel here. I draw the next point. I see that I've drawn something else in that pixel before, so I just increase the counter to 2. And as you can imagine, I keep doing the same thing for all my points. And in the end, once I've drawn everything, each pixel of this canvas contains the aggregate of all the points falling in that pixel. So in this or in this example, I used the count of points as my aggregate because we have a count query that we want to evaluate. But you could apply some other aggregate function as well. For example, if you want to find, so you have the pickup location of a taxi ride, but this can have also other attributes associated with it. For example, what was the price of the ride? So you could compute the average of that price, for example. But here, of course, I'm not done yet, because what I want is to have the aggregates in each polygonal neighborhood, not inside all these pixels. But I can calculate that aggregate by drawing the polygons on that same canvas. So this is one of my polygons, and now you can think of this drawing as coloring all the pixels that are covered by that polygon. So here I start coloring the pixels of the polygon, and as I paint them, what I can do is that I can aggregate the partial aggregates that these pixels contain here. So then I keep a counter for the polygon. So here I start with the first one that we don't find any number in it. Then I draw the next pixel and I see that there is a count of 2 inside that pixel. So I add it up here. Then there is nothing in the next one. Then I find 1, I add it up. My counter for the polygon becomes 3. And again, once I've examined all the pixels that are covered by my polygon, I get here a total of 15, which is the final aggregate result for this polygon. Now, is it really the final aggregate result for the polygon? Well, if you look a little bit more carefully, you will see that, in fact, I did my aggregation operation over a pixelated version of my polygon, which is essentially an approximation of my polygon. And this is the region that I show you with purple color on the slide, which is not exactly the same as my original polygon. So as a result, what can happen again here is that I might have some points, like the 2 that I'm showing you with red color on the slide, that I count them, although they are not inside the actual polygon. Now, a key observation here, though, is to see that if I have such errors, this can only happen around the boundary of the polygon. If a pixel is completely inside the polygon, well, whatever point falls in that pixel should also be completely inside the polygon, and there is no doubt there. So if you want to compute an aggregate result, an accurate aggregate result, you can exploit this inside and first separate, identify which are the pixels that that fall on the polygon boundary, and which are the pixels that are fully enclosed inside the polygon. And then in this case, what you can do is that only for the pixels that are around the boundary, you do this point and polygon test to really test if the point is inside the polygon or not. But you only do this for the boundary area, and for the rest, you can already just take the counts from the pixels as I showed you before. So this approach works quite well, because here we frame the problem of evaluating spatial aggregation as drawing operations, and these are highly optimized for the GPU. And we minimize the number of point and polygon tests that we need to perform by doing such tests only at the polygon boundaries. And another property here is that we actually combine the join and the aggregation in a single operator, which means that we don't really materialize the join result. We don't need to know as an intermediate result which is the point that is inside which neighborhood. We just directly count everything inside the neighborhood. So as you saw just now, the approach that I described computes an accurate result. But let's go back to our application and then ask ourselves if this level of accuracy was actually necessary. So the first thing about visual tools is that, in fact, they are approximate in nature, because in the end, small differences in the aggregate result might not alter at all the visual representation that you see on your screen to an extent that the naked human eye can notice. So, for example, for heat map, we just map the counts to different colors. So if the count is slightly different, but in the end it's still mapped to the same color or to a color that's like super close to the original one, well, you're not going to visually see the difference. The other observation is that typically as a user of a visual system, you do level of detail exploration, which means that you start with a more high-level overview, where again the low-level details are not so important, and then you typically zoom into smaller regions to get more accurate results. So again, for this high-level thing, it might be okay to be less precise. And last observation is that actually spatial data is not 100% precise inherently. So GPS locations, for example, are not 100% accurate. The accuracy that you get today is like within a 5-meter radius. And the same goes for region boundaries, because these are kind of artificially imposed in a sense. So if you look at the region boundary between two neighborhoods in Manhattan, this is typically a street, but the street is not just a one-dimensional line. It kind of has a width, and if we are talking about a big avenue, it can be a relatively big width. So if a point really falls at the boundary, like semantically, it might be okay if you count it or not, or if you count it in the one neighborhood or in the other, right? So it doesn't really, it's not really an error in practice. So taking all that into account, let's now not obsess so much over accurate results, and let's start thinking about enabling approximate queries. So then we could get an sufficiently accurate approximate result than if we just evaluate the query over the approximate purple polygon rather than the original one. But then what is missing here to make this approach useful is that we want to provide some guarantees on the spatial distance between the original polygon, where that was in our input and we were supposed to calculate the query over it, and the approximate geometry that we are using in the end, so that the user understands how closely the approximate results correspond to the actual specific spatial region that she's interested in. So for that, we can measure the distance between the two geometries, so the purple approximate polygon and the original polygon, using the Hausdorff distance. And then what we want to achieve is that we want to have a bound on that distance between the two polygons. And then we can either calculate this bound and return it to the user so that they know the accuracy, or even better, we could allow the user to control this bound and define how accurate the result should be. And what happens here intuitively is that if we use a smaller pixel size, so if we do this drawing at a higher resolution, then the pixelated purple polygon will approximate our original polygon more closely, and as a result, overall, we will have a higher accuracy. So that's how we can manipulate this bound. Okay. So here in the end, if we do that, we can be significantly faster than the approach, the exact approach I presented before, because now we can skip point and polygon tests altogether. And this is a trade-off between the accuracy that you have and the response time, for how fast your query can be. All right, so this is, actually my last slide. I finished a bit faster than expected, but I also have some performance numbers. If someone is curious, maybe I'll keep them for the Q&A. So let me summarize, I guess, here so we can have some time for questions. So what I presented to you today, other than a high-level overview of the spatial databases, the spatial data primitives, queries, and the filter and refine evaluation pipeline that we use, is spatial approximations and how important the precision of the spatial approximations is, and how increasing the precision with a few tricks can make a difference in query performance. And then I discuss how we can express queries as graphics primitives that enables us to leverage modern GPUs. And in the end, I talked about using a distance bound so that we enable approximate evaluation, which unlocks another level of boosting performance by eliminating expensive tests. So thank you. And now we can have some questions.